Welcome to the video about finding the moment of inertia of a solid disk or a cylinder. We are going to find the moment of inertia of this solid disk or cylinder by dividing it up into pieces that are all equal distance from the center of mass. The center of mass of the disk is at the center of the circle, and to find the moment of inertia we need to integrate r squared times dm, where r is the distance of the entirety of each piece dm from the center of the circle. And so to do that, we are going to divide this up into thin rings of radius r, which is our variable. So here's the radius r of the ring, and the thickness of the ring is dr. So the ring radius is our variable r, and the thickness is dr. So first thing we have to do is find dm. So dm is equal to the density times the area. Sigma is the mass density of the disk, and dA is the area of the little ring. So the mass density is the total mass divided by the total area. Sigma is an area density, unlike lambda, which is a length density. So the total mass is m, and the total area is pi r squared. So our density is m over pi r squared. Now the area of the ring is relatively easy to follow if we make an assumption, and that is that dr is relatively small. So basically, if we slice this at one point, we can stretch it out, and the dr is small enough that the inner radius and outer radius are pretty close, and this can be estimated to be a rectangle. And that rectangle has the length that's equal to the circumference of the circle, which is 2 pi times the variable radius r, and the thickness is dr. So the area of this, if it's small enough, if it's thin enough, is equal to 2 pi r dr. So now I'm ready to do my integration. The moment of inertia is the integral of r squared dm, which is the integral of r squared times sigma dA, the density times the area, which is the integral of r squared times sigma, which is m over pi r squared, times dA, which is 2 pi r dr. So some of these letters in here represent constants, things that don't change as I change the radius of my circle, and so therefore those can be pulled out of the integral. But first, note that pi cancels out, and so we don't have to carry that around anymore. So basically the constants are total mass, 2, and total radius squared. So 2 times total mass over total radius squared, those are the constants, and the integral is left r and another r and dr, so r cubed dr. And I'm going to add up all of the little circles, starting at a radius of 0 and going to the total radius of the disk. So my limits on integration on this variable are 0 and capital R, my total radius of the circle. So 2m over r squared times the antiderivative of r cubed, which is r to the 4th over 4, and I evaluate that at the limits 0 and r. So we have 2m over r squared, plug in our limits, capital R to the 4th over 4, minus plug in 0, 0 to the 4th over 4, and we're left with 2m over r squared times r to the 4th over 4, which simplified gives us 1/2 mr squared. So therefore the moment of inertia of a disk or a cylinder with the axis at the center is equal to 1/2 the total mass of the disk times the total radius of the disk. So that's half of what the moment of inertia of a ring or a hoop would be of the same mass and radius.